Hi, I'm Andy Sellers, an application engineer at Typhoon Hill. I'll be taking you through our grid modernization demo series. For the series, we'll be using two of our Hill 604 ultra-low latency hardware-in-the-loop simulators. These on their own are an industrial workhorse, or they can be parallelized to simulate even larger systems. We'll be making use of three of our modular Hill Connects. These Hill Connects act as signal conditioning. They take input and output from our Hill simulators and actual hardware controllers, which will be deployed in the field. By using these Hill Connects, our Hills are able to keep safe operating values in terms of voltage and current at their outputs, and our controllers are able to see the same voltage and current levels they expect to see in an actual application. For our controllers, we have an SEL 451 Bay controller, two SEL 651 reclosers, an SNC IntelliCap 2000 capacitor controller, and a Beckwith M2001C tap changer controller. These will be interfacing with a simulation of a distribution system, which consists of two feeders, each fed by a grid at 12.47 kilovolts. Each of these feeders is broken into a number of zones separated by feeder protection relays, and the two feeders are connected by an intertie. Each of our relays are controlled by either a software controller or one of our hardware controllers seen here at the top. The system is also capable of volt-var regulation, again through a combination of software controllers and our SNC controller. Voltage regulation at the substation level is handled with the Beckwith M2001C tap changer controller. Now, if you'll join me on my computer, I can take you to the software side of this.
The system I'll be using in this series is a medium voltage distribution system. It consists of two feeders connected through a normally open intertie. Each of the feeders operates at a grid voltage of 12.47 kV or 7.2 kV phase to neutral. The feeders are supplied by a substation, modeled as a VBR or voltage behind reactance grid, a meter, an on-load tap changer, and a disconnect. Both a tap changer and disconnect have associated controllers, and in the case of substation 1, these are both hardware controllers. A Beckwith M2001C tap changer controller is used to control the tap changer, and an SEL 451 Bay controller is used to control the disconnect. Each of the feeders are divided into a number of zones using feeder protection relays. These relays are either simulated using signal processing based controls, or an external controller is used, in this case two SEL 651R reclosers. Each zone consists of some combination of loads, either classified as industrial or residential, switched capacitor banks, either controlled with an internal signal processing based controller or a hardware controller in the loop. In this case, an SNC IntelliCap 2000 capacitor controller is used, meters, and regulators. The loads in the system are modeled either as constant impedance loads, set to have a fixed power draw at a known power factor at nominal voltage, or as VBR variable loads. Fault components have also been placed throughout the system in each of the zones. These components allow us to simulate faults in the system during simulation and analyze system response as well as controller behavior. Coupling elements used in the system allow us to divide the model onto the various FPGA cores of the Hill simulators in the case of core couplings, or to divide the model onto the two devices in the case of a device coupling. We can run the simulation and interact with it through our Hill SCADA. From SCADA, we're able to run the simulation and interface with the model and the controllers. At startup, the system goes to its nominal operating condition at a grid voltage of 12.47 kV. Our normally open intertie is in its normally open state, and each of our other relays are closed and conducting. At the bottom of the panel, we have a set of groups for the soft relays. These give feedback on error state of the relay, whether it's in sync check or not, and voltage on the grid-facing and feeder-facing side of the relay, as well as current through the relay. If a fault causes the relay to trip, we can reset it using this reset option. We can also force a fault in the relay, forcing it open or closed using this combo box. This allows the relay to either be forced open and unable to reset, or forced close and unable to trip properly. These can be used for redundancy tests. Hardware controllers can be seen in their individual subpanels. Here we can see the subpanel for the SEL 451 Bay controller and outputs coming from that controller. Variable loads have also been used in the system and can be interfaced through their own subpanels. One load has been implemented as a time-varying load. In this case, this load follows a predefined load profile in real time, altering its active and reactive power. Similar techniques can be used to have models of solar panels follow irradiance profiles, or to simulate any other type of time-varying load. A second variable load has been implemented as a controllable load. In this case, the load value, both active and reactive power, can be specified using sliders in real time. Options have been included to toggle zone faults, to trigger the fault component switches seen in the schematic, and buttons have also been included to trigger various system states, in this case, low and high voltage conditions on each of the feeders. A scope capture widget has been included as well to probe the system at the level of the electrical solver. Using this tool allows you to inspect the system the same as if you were using an oscilloscope on a physical system. From here, we're able to run a number of useful and interesting tests. If you want to see the response of a relay to a fault, for instance, we can look at R2. Here, this scope capture tool is set to view the voltage on the grid-facing side and feeder-facing side of R2, the current passing through R2, and here we have a secondary voltage in terms of RMS on that relay. If you go to the capture tool, we can import scope settings, and this will allow us to capture the same 4 signals seen on the scope window. When we enable the trigger, we'll now wait for a falling voltage on the secondary side as configured through our trigger window. And if we toggle a zone C fault, we can see that we've caused R2 to trip, zone C to go to 0 volts, and we should have triggered our capture window as well.